This video's problem deals with a little bit of a tricky breakdown in logic. In particular, I'm going to show you guys how to solve section H problem 3. And in your homework, basically what you're going to do is read between the lines on the proof that I show here and figure out what changes when I mess with the hypotheses. So let's be a little bit specific and write on the problem statement. So in the problem setup, we have a finite set. B is some subset of A. And we look at the subgroup of SA with the following property. Actually, I'm realizing that I said subgroup, but the exercise is to prove that it's a subgroup. I think it's okay. The subgroup in question is the set of permutations of A such that permutations F of A such that if B is an element of B, then F of B is also in B. And your homework problem is to figure out where this finiteness is crucially used, and in particular, find a counterexample when A is an infinite set. So I'm going to give you guys an explanation of this. And I don't want to say I'm going to cheat. I think if you listen carefully, you'll be able to figure out kind of how I'm using the finiteness. But then the question is, what changes when it's infinite? And so let's recall what we have to prove. I need to prove this is a group. So in particular, the associativity is clear because it's a subset of permutations. Those are functions. They compose in an associative way. We need the neutral element, and we need the inverses. So for the neutral element, I claim that it is obvious, and of course I'm going to explain at least a little bit afterwards, that the neutral element is here. The reason I claim it's obvious is because the neutral element does nothing, and so in particular, every B is sent to itself. So of course this property holds. For the inverses, we have the following logic. Every set has an every permutation in SA has an inverse permutation. Permutations always exist. The question is, why is F inverse also an element of G? And here is my argument. Since B is a subset of A, and we have bijectivity of A, and also we have injectivity in B, we have surjectivity in B. This is my hint for your question. Why is this true? But once I know this, I have bijectivity in B together. And so, in other words, every permutation in A splits, into a permutation of B and a permutation, not in A, and G. Of the rest. So therefore, since you're a permutation of B, F inverse also permutes B. And we're done. Okay, so your task then is to figure out how I pulled off this sleight of hand and use that observation to break this logic when I remove the assumption that A is a finite set.